Hello everyone, I'm Jianjun Chen. Welcome to this talk. Today I'm going to share our latest work about email spoofing attacks. Email is widely used in our daily life and is a frequently used attack vector for various attacks. In the past years, we have seen numerous attacks using email spoofing and phishing attacks to compromise enterprise networks or government official accounts. To address this problem, modern email services and websites deploy sender authentication protocols like SPF, DKM, and DMARC to prevent email forgery. In this talk, we will present a number of new techniques to defeat those defenses. This is a joint work by 3 authors. I'm a postdoc at IGSI focusing on HTTP and email security. Vern Paxson is my supervisor. He's a professor at UC Berkeley and the original author of the Brawl ideas. Based on the Brawl system, he created a startup, CoreNet, which provides high-performance network traffic analysis solutions. Jian Jiang is the senior director of engineering at F5. He has done some influential work in DNS and web security. Okay, first, a quick question. When you receive an email, how do you tell whether it's a phishing email? Normally, we would check the from address displayed in the email client. If the from address is legitimate, we may believe it's not a phishing email. If we use email services like Gmail, we can also check additional security indicators like mailed by or signed by to verify the sender. In this talk, we are going to present a number of new techniques to spoof those security fields. Here is a spoofing test I did several months ago. Gmail shows that this email is sent from security@facebook.com and verifies that the email is signed by facebook.com. But in fact, it was spoofed by me. How could it happen? Why Gmail didn't reject this message? We will answer these questions in this talk. To understand this attack, we need to know 2 important concepts in the email protocol, sender and authentication. Let's look at the first one. Here is an email example we often see in our daily life. Who is the email sender? The from address we often see only represents the user who composed the message. There is another invisible part called SMTP envelope. The hello and mail from address in the SMTP envelope represent the user who transmitted the message. This design is similar to the mail in our real life. The address in the envelope and address in the message data can be different. This picture shows how an email is transmitted on the network. First, Alice logs in her sending service to send an email. Then the email is sent to Bob's receiving service. Then Bob retrieves the email using his email client. When SMTP is originally designed, it has low built-in authentication mechanisms. Anyone on the internet can claim another's address in hello, mail from, or from field. For example, an attacker can claim he is Alice at a.com and send a spoofing email to Bob's receiving service directly. The receiving service cannot tell whether the email sender is really Alice at a.com. To address this problem, various email authentication mechanisms have been proposed. SPF, DKM, and DMARC are 3 most widely adopted protocols. SPF verifies the sender IP address. DKM verifies the email signature. DMARC is designed to fix the alignment problem in SPF and DKM. We will talk about the alignment problem later. Let's look at how those 3 protocols work. First, SPF uses IP address to authenticate the sender. It works in 3 steps. First, the sending service publishes DNS record to specify which server IP are allowed to send the email for this domain. When receiving the email, the receiving service will query the domain in hello and mail from field to obtain the IP list. Then the receiving service will check whether the sender's IP matches with the obtained IP list. If yes, SPF pass. So SPF ensures that only authorized IP can send the email for this domain. DKIM uses public key cryptography to authenticate the sender. It works in 4 steps. First, the sending service publishes their public key in DNS record. When sending an email, the sending service will use the corresponding private key to sign the message to generate the DKIM signature header and attach it to the message. In the DKIM signature header, 2 tags are very important. D tag represents the signer's domain. S tag can be any character. It's used for a subdomain. When receiving the email, the receiving service will query s.domainkey.d to obtain the public key. S and D are extracted from the DKIM signature header. Domain key is a constant. For example, in this case, the receiving service will query any.domainkey.a.com to obtain the public key. Then the receiving service will validate the DKIM signature with the obtained public key. If the signature is valid, the email passes DKIM authentication. So DKIM ensures that only the person who knows the private key can send the email for this domain. Unfortunately, neither SPF nor DKIM provide a complete solution to prevent email spoofing, because SPF verifies the hello and mail from identifier. DKIM verifies the DIC field in the DKIM signature header. Neither of them verify the from address that is displayed to the end user, which means even if an email passes both SPF and DKIM validation, the from address can still be spoofed. DMARC is designed to fix this problem. First, when the sending service publishes DMARC policy, the receiving service must perform identifier alignment test to check if the from header domain matches SPF or DKIM verified domain. Match means exactly match or have the same registered domain. Another important point is that DMARC only requires either SPF or DKIM show a positive result. This design is intended to provide more robust list. For example, for forwarded email, SPF may fail, but DKIM will survive. If both SPF and DKIM fail, DMARC fail, then the receiving service will enforce the policy specified by the domain owner, such as rejecting the email or sending failure reports. Here is an email authentication flow. When the receiving service receives an email, SPF component will check hello and mail from identifier. DKIM component will check the DKIM signature header. DMARC component will check alignment with the from header. If the email passes either SPF or DKIM authentication and the from header passes the alignment test, the email passes DMARC authentication and then is delivered to the end user's MUA. So the flow sounds good. What could possibly go wrong? We found 18 attacks to bypass the authentication. The key idea of our attacks is to exploit inconsistencies between different components. As shown in the picture, an email sent by the sender's MUA needs to be processed at least 6 different components before reaching the recipient. Those components are often built by different developers or different companies and have a wide range of inconsistencies, which can be exploited by attackers. An attacker can craft an ambiguous message with multiple identifiers. Component A may take one identifier, but component B may take another identifier. This can cause semantic ambiguity and lead to authentication bypass. In the following talk, we will talk about several examples to illustrate the problem in detail. The first example exploits inconsistencies between SPF and DMARC. SMTP define two different identifiers, hello and mail from, to represent the user who transmitted the message. SPF standard require SPF verifiers to check both of them. If either fails, SPF fails. DMARC standard require DMARC verifiers to use the mail from for the alignment test. If mail from is empty, then use hello. The problem is that if SPF verify hello and DMARC use mail from to check alignment test, it can cause ambiguity to bypass the authentication. Here is one case we found. An attacker set the mail from to be a line exist subdomain. SPF component cannot verify the mail from address and can only verify the hello identifier because non-exist subdomain doesn't have any SPF policy. Then the SPF component will forward the hello authentication results to DMARC. DMARC component, however, still use mail from domain to perform alignment test because mail from is not empty. So in this case, SPF will pass because hello domain is under attacker's control. DMARC will pass because mail from and from header has the same registered domain. The second example exploits inconsistencies between DKM and DNS. This is the bug we demonstrated at the beginning of this talk. Here is how the attack works. First, an attacker constructs a spoofing message and assigns the message with his own private key to generate DKM signature header. In the DKM signature header, he specifies the D tag value as bank.com and the S tag to include a null character. When the receiving service receives the email, the DKM component will query s.domainkey.d to obtain the public key. But when the DNS component resolves this domain, it passes the null character as a stream terminator. So the public key is actually obtained from attack.com. So in this case, DKM will pass because DKM component use attacker's public key to verify attacker signed message. DMARC will pass because the D tag domain is equal to the from header domain. The third example exploits how SPF and DKM forward authentication results to DMARC for the alignment test. RFC defines authentication results header for communicating those results. Here is an example of the authentication results header. In the header, smtp.mailFrom and header.d represent the SPF and DKM verified domain. So the DMARC component will extract those two values to check alignment with the from header. Another important information in the header is the parentheses. The content in the parentheses means a comment, which should be ignored by DMARC. Here is an example we found to exploit this forwarding process. First, an attacker constructs a spoofing message and assigns the message with his own private key to generate the DKM signature header. In the DKM signature header, he sets the D tag value with an open parenthesis embedded in it. When receiving this message, the DKM component queries s.domainkey.d, which is attacker's domain, to obtain the public key, and generates the following authentication results header. When receiving the authentication results header, the DMARC component parses the content after the parenthesis as a comment, and take bank.com as the DKM verified domain. So in this case, DKM will pass because DKM component use attacker's public key to verify attacker's message. DMARC will pass because DMARC component use the first part of the D tag domain to check alignment with the from header. Similarly, an attacker can also set the parentheses in the mail from field to bypass the SPF and DMARC authentication. SPF verifies the entire domain, but DMARC only takes the first part for the alignment test. In addition to the parentheses, an attacker can also use a single quote or double quote to replace the parentheses. Okay, in the previous slides, I presented 3 attacks that exploit inconsistencies in a single implementation. In the following talk, we will show attacks exploiting inconsistencies across different vendors, which are more diverse and hard to be fixed. Now I will hand it over to Jen to show how those attacks works.
Thank you, Jianjun. Next, I'm going to present a number of attacks we categorize as UI mismatch attacks. In this attack, the attackers will craft email messages that containing 2 identifiers. One is the attacker's identifier, another is the spoofing identifier, in the way that receiving service will recognize the attacker's identifier and for verification and pass the verification. However, the recipient's MUA will pick up the spoofing identifier and display it to the recipient. So the first example, the attacker will just simply send an email with 2 from headers. The first is the attacker's email address. Another is the spoofing target. So the receiving services DMARC components. In some of implementations, they will just pick up the first header and verify that, and that will pass, of course. So, but some of those mail user agent will pick up the second one to display, and that causes the phishing effects. Some of those combinations are not vulnerable to this simple format, but we find other variations that are able to attack those. So one of those variations is that you could use a 9-folding format in the first header, and some of those DMARC implementations will recognize the 9-folding format and still verify that. But for some of those mail user agents, well, even they are programmed to pick up the first from header, but in this case, they consider this 9-folding from header is invalid. So they pick up the spoofing identifier to cause the attacks. Another variation is to utilize the normalization behaviors. In this case, the attacker sent still 2 from headers. The second one is containing a space in the header name. The receiving service will recognize the first one and verifies. It actually won't able to recognize the second one as a valid header, but when it forward to the MUA, it actually normalize the header and to remove the space. And the MUA will pick up the second one to display. The previous examples use from headers, multiple from headers. Actually, there is another technique you could use some other headers. In the email protocol, it defines 3 types of headers that you could put sender identifiers in. There's from, sender, and resend from. So for some of those MUAs, you have this kind of implementation behavior that if they cannot find a from header, they will display sender or resend from. So in this example, we show that the attacker crafted a 2 headers message. One is from with a 9-folding format, another is sender. And the DMARC implementation will be able to recognize the from in that format and verify that. However, the MUA won't be able to recognize the from, so it will think this email does not have a from header, then it will display the sender header here. There are some other variations of this type of things, of multi-headers, but not only just you could send the multi-headers to create these ambiguities. Even you only allowed to send one from header, it's still possible to create this type of ambiguities because of the parsing complexities. Take a close look of the from header syntax. It is actually surprisingly complex. So the from header is defined with 4 portions, and each portion you could put some kind of identifiers in different places, and the parser needs to be correctly picking, in this case, a@a.com as a real address, but many parsers behave differently. In addition to that, there are a number of string-related kind of traps that could make things even more complicated. For example, you could have Unicode characters, you could have like encoding, you would have those kind of special characters put in those from header values to complicate the parser. We actually find many cases that you can craft to create this type of inconsistencies between the mail server and the email client to launch the UM mismatch attacks. The first example we wanted to show is you just simply put 2 identifiers in the from header, and some of the implementations will pick the first one, some of those will pick the second one. Next example is you could craft a from header with the route portion, and some of those implementations, they will correctly recognize this is a route portion, so they won't pick up, they will pick up the first one as the identifier, but some of those implementations, they don't support route portion, they will just think this is the second one as the actual identifier. And you can also use base64 encoding to send multiple identifiers, and some of the implementations, they will try to do the base64 decoding so that they could recognize the encoded identifier, but some of those implementations won't, so that they can only recognize the non-encoded identifiers. That also creates a inconsistency spaces. There are some other kind of format to create this type of inconsistencies, like using special characters and so on. So I'm going to skip those details. Actually, we found this UM mismatch attacks is prevalent among the combinations of those implementations. And we found 43 out of 82 different combinations that can be exploited in certain ways. And our test is actually not compressive, that are likely more cases of those things. Please read our papers for more details about this attack. The previous attacks is actually not perfect in that if a user is careful enough, they will check the indicators. They will say, although it is displayed as a spoofing identifier, but it will show that it is either signed or sent by the attacker's domain. However, there are certain other kind of attacks we found that could have the spoofing identifier and the attacker's identifier share the same domain. For example, if some attacker at gmail.com can spoof an email from admin@gmail.com, that could cause same amount of damage as is spoofing at different domains. So how those attacks can be launched? of course, you could think about you might be able to simply log into like an email provider like a Gmail and try to send an email using the admin@gmail.com. But that simple attack won't work most of cases because the sending service will likely to perform some kind of verifications on the claimed from header so that it matches the actual user account. But since we have presented the parsing and the extracting of the identity is actually a complex process that the sending service can also make mistakes. So using the previous techniques, that one attacker could create a situation that the sending service will think it verifies as the attacker@gmail.com as the sender identity, but however, the MUA will pick up another one, for example, admin@gmail.com as the displayed sender. And in this case, because of the attacker's domain and the spoofing target's domain is the same, so even you check those security indicators, you won't be able to recognize any kind of suspicious evidences. And we actually found using the previous techniques to craft the email, 7 out of 8 email providers are vulnerable to this type of attack. And one exception, email provider is actually not vulnerable because it will always try to reset the from header, no matter how you craft from and the sender those type of headers, they will just reset the from header as the actual user account, which in this case, the attacker's account. With that kind of defense, forces us to think more about how we can actually attack that particular email providers, and we come out with a more complex format of attack. So this attack combines 2 steps. The first step is that the attacker will log into this email provider and send to himself an email crafted using this format. And the from is attacker@gmail.com, and the to is victim@victim.com. But since in the envelope, the receipt to is attacker@gmail.com, so this mail is actually going to be delivered to the attacker himself. And in addition, this email provider will actually provide a valid DKIM signature by signing the from, the to, and the content. So in the next step, the attacker will using his own email server to send the signed email with a small tweet. The small tweet is to add another from header. So it actually goes back to our previous attack techniques. Is this additional from header creates a ambiguity between the receiving service and the MUA of the victim, in that the receiving service will verify the DKIM signature using the attacker's identifier, which is the original assigned identifier, so that the DKIM verification will pass, and the MUA will display the admin@gmail.com in this case, and then that will becoming a spoofing email to the victim. With all of those attacks, we consider this, why this could happen. I think the ultimate problem is the complexity. So in the email protocol, we think there are three sources of complexities. One is that you have multiple identifiers in the email protocol, and it is easy to have discrepancies, inconsistencies of which identifier to use. The second is the syntax of the identifiers can be complex, that the parsing is not easy to make it right. The third one is that in the email systems, one email message is processed by multiple components, and all of those components need to have some kind of agreement on the identifiers they recognize, so that the whole some of those assertions, security assertions, could be held. Those are the sources of those inconsistencies come from, and from a defense perspective, you should just make it simple to remove those complexities. What we think is that when you design a protocol, not only you wanted to make the protocol to be correct, but also wanted to make the protocol to be implementation friendly, make it simple, make all these messages well typed and easy to parse. And you also should try to reduce or avoid multi-party processing, that you need a multi-party to have some agreement. Two parties is good enough. If you have three party, four party needs to agree on something, that likely to have some issues. And generally, when you do the parsing, you should be strict on what you accept and reject any kind of suspicious format you would like to avoid this kind of parsing issues. The second point we wanted to bring up is that we found the user interface of email is not sufficient to have some kind of a security assurance. So even for a security professional, it's not easy for them to use any kind of security indicators to show this, if this email is trustable or not. I think there are plenty of spaces to improve in that direction. Finally, for the end users, we would like to remind that don't blindly trust the email displayed in your web mail or email clients. Try as much as you can to verify whether this email is trustable. And also, we wanted to advocate using PGP as a secure email mechanism, because PGP, the authentication in PGP is much simpler in that it provides an end-to-end authentication only involving two parties, and also the identifier is more likely more robust from those inconsistencies. It can have its own problems, but hopefully better than the traditional standard email protocols. We have connected all of those test cases and put it together into a tool we publish on GitHub. For those interested to play around, please check this link. That's our presentation. Thank you very much.
The responsible disclosure. Yes, we have disclosed all the attacks to the affected vendors, and we actually tested 10 email services and 19 email clients, and most of them respond our report positively, and all except Microsoft and Yahoo said they are fixing them or they have fixed them. And Microsoft said didn't consider this report as a valid security report because they don't consider the social engineering attacks as a security vulnerability, because this email spoofing is often used for phishing attacks. Yahoo didn't consider these attacks because they think our attacks rely on DNS misconfiguration. So they just ignored my report. The second question is, has this report been discussed in IETF? Yeah, we didn't report this paper to the IETF, but I searched our paper on the internet and found there was a discussion in the DMARC working group, and they feel this is an implementation issue rather than a specification issue. So probably they have discussed this. I'll post the discussion link in the chat box.
Related to that, Jianjin, there's a question about if DKIM, SPF, DMARC are all properly implemented, and if the MUA has strict for all RFC compliance, can email still be spoofed?
Yeah, it depends on what do you mean by properly implemented. Our attacks exploit inconsistencies between two different components in the email processing chain. So some messages are actually valid messages. For example, a message with a from header with two address in the from header. And this is actually an RFC compatible message. And but different components may recognize a different identifier in the message. For example, the email server may recognize the first one, MUA may recognize the second one. So, yeah.
Let me answer another question, which is, has there been any effort to make Zeek or Snort detections for these techniques? I can't speak to Snort. Zeek, of course, is near and dear to what I do in Corelight. And from Corelights perspective, no, not yet. And the main reason is we rarely have visibility into clear text email on the wire. It's usually inside TLS. And so there's not an opportunity to look for these things. In environments where that changes, it would be interesting, certainly, to code up such techniques.
Okay. Yeah, we have so many questions and so little time. Yeah. But we will answer the question in the channel after this video, in the chat box one by one, and feel free to follow the Twitter on Corelight or my Twitter to ask me any questions, and we will also provide all the materials such as papers, our tools, and slides if the black hat, and slides in the chat box. So or make a tweet about those materials.
Great. Thank you very much, folks.
Yeah, thank you.